Hello everyone. Today's big question is what makes a magnet a magnet? Where does magnetism come from? How come certain things are magnets and certain things are not magnets? All right. So it's a pretty interesting question. You've dealt with magnets your whole entire life, but unless you really understand the physics, it seems like it's magic. All right. So let's answer that big question. What makes a magnet a magnet? And we're going to start with that is, where does magnetism start? All right, what caused it? Well, it's actually a pretty easy answer. It's a moving electric charge creates a magnetic field. Now, anything that creates a magnetic field is a magnet. So a moving electric charge is a magnet. Now, why does that happen? Well, that's explained with Einstein's relativity, and we don't have time to go into that. That's a whole other subject we have to learn before we can see how that applies here. All right, but the whole idea of magnetism starts with electric charges. All right, and you can start to see now why we say the branch of physics is electricity and magnetism, ENM, not just electricity, not just magnetism, but together. All right, and you're going to start to see how interrelated they actually are. So remember, magnetism starts with electric charges, but they have to be moving. That's the big key. So an electron by itself is not a magnet. It's just sitting there doing nothing. It's not a magnet. But an electron that's moving, hence its velocity vector, is a magnet. This thing will create a magnetic field. This thing will be affected by magnetic fields. This thing won't interact with a magnet at all, but this thing will interact with the magnet. And we'll see that interaction later when we start to look at some of the equations of that. All right. So again, a moving electric charge is a magnet, and we're going to focus on the electrons because the protons are, again, they're stuck at home in the nucleus. All right. So we're pretty much going to be talking about electrons. Now, that idea that magnetism starts with moving charges is all well and good for me to say that, but I still got to be able to prove it. So let's figure out a way to make sure that's actually the case, as opposed to this being just some dumb YouTube video where people post on Facebook that's not real at all, but everybody believes it. But that's a whole another issue. All right. So let's do a little connect the dots here. We know a lot of flowing electrons is a current. All right. And so therefore, a current must also be a magnet. Well, we can test that out. We can see if that works. And I'm going to show you in this demo here. Let me get this all set up for you, and I'll prove how electricity essentially can act as a magnet. Okay, here you can see I have a piece of iron wrapped with a copper wire. All right. Now there's obviously no current flowing through because it's not hooked up. And you can see from this compass that it is not being affected. The compass isn't being affected by this thing. So this thing right now is not a magnet. All right. We can see that because if it was, all right, the compass would be affected by it, just like a regular magnet. All right. But now what I can do is I can hook up some wires to it, all right, and pump some current through here, and let's see what happens to the magnet, or sorry, to the compass. Because if this thing all of a sudden creates a magnetic field because current's going through there, then this thing would be caught up in that thing's magnetic field. So I'm going to turn this on. All right, get some current going through there. And yeah, now we got current, and you can see this would be a magnetic pole. As we move this along, all right, it stays pointed at the magnetic pole, and it will switch over to the other magnetic pole here. All right, so that's proving that the current is making a magnetic field. In other words, this current going through here is now acting as a magnet. All right. Now, what this thing essentially is an electromagnet. All right. I'm making magnet from electricity, and there's two major advantages to that. Is that I can control, well, I guess it's just one advantage. I can control the strength of this magnet, all right? If I want it to be stronger, I can just turn up the current, all right? Now, the other really nice thing about electromagnet is the ability to turn this on and off. If you have these solid state magnets, like here, they're always going to be magnets. There's nothing I can do. I can't turn these off, or on. But for this electromagnet, all right, I can turn it on, and then, so we can move this over here, see it's a magnet, right? I can turn it on, and I can turn it off, all right. Okay, now that we've seen current does create a magnetic field, the next question would be, well, what about these magnets, all right? Clearly there's no current running through here, all right? So what makes this a magnet? Well, go back to the beginning. Moving electric charges create magnetic fields. So let's break this down to the smallest thing that we study, which is the atom, all right? So in the atom, we know that the electrons orbit the nucleus, all right? So that orbiting means moving electrons, and so therefore an atom has moving electrons, therefore an atom is a magnet, okay? But the other thing is that we never, that's not studied that much, is electrons also spin. Now spin we know is movement, all right? So electron spin also means it creates its own magnetic field. Turns out the electric spin magnetic field dominates just the orbital magnetic field. This is the one that's really important. It's a lot stronger for whatever reason, okay? So now we know, according to this, each atom has its own magnetic field because it has electrons that spins. All right, so that makes sense, but until we examine it in our everyday lives. Everything's an atom, so why isn't everything a magnet? And we know everything isn't a magnet. We can test that out. Look, here's a book. Here's a magnet. Magnets exert forces on other magnets. This is a magnet, and this is a magnet that would exert force on each other. Clearly that doesn't work, all right? So one of these two things is not a magnet. Well, we know from experience now that these two things are magnets, all right? Well, what about this? Here's a copper tube. This thing's metal. This thing is not metal. So, oh, well, it's metal. It's magnetic. It's a magnet. Nope. Copper is not a magnet. It is not magnetic. All right, look, doesn't work. So what makes this a magnet? What's special about this than all these other things? Because they're all made of atoms, and atoms have electron spins, and electron spins create a magnetic field. All right? So let's investigate that further. Okay, when we look at electron spins, turns out electrons will spin in different directions. You can imagine them and visualize them as maybe one electron in the atom is going clockwise, and maybe the other electron in the atom that's orbiting is going counterclockwise. All right, it's two different spins, and that's going to make two different magnetic fields. All right, so if the electron spins are similar, all right, they will combine their magnetic fields and make a bigger magnet for that atom. All right, if they're opposite spins, then they'll just cancel each other out. All right, turns out that in almost all atoms, with the exception of a few, the electron spins cancel out. So you would think, since each atom has moving electrons and spinning electrons, that each atom would be its own magnet. Turns out that's not the case. All right, the individual charges that are moving are creating a magnetic field, but as a whole, those magnetic fields cancel each other out. All right. Now, the exception to the rule, or not to the rule, but the exception in experience is the atoms of iron, nickel, cobalt, and there may be one or two others. But the main one we'll focus on is iron, because we make steel from it, and that's what we generally use when we talk about magnets and magnetism. So in those atoms, of course, remember, still at the atomic level, those few elements are, so there's few elements, their atom is a magnet, all right, because then it makes its own magnetic field. But then there's a bigger question, all right? If we keep going on this experience, and I'll show you that here in one sec. Okay, now we've seen iron that is not a magnet, all right? Well, that seems it's contradictory to everything we're talking about. If an iron atom is a magnet, then something that's made of a whole bunch of iron atoms, that should be a magnet as well. Not necessarily, okay? So if we look at the individual atom, yes, it is a magnet. And it's based off the direction of the electron spin. Well, you can imagine that individual atoms can have electrons that are maybe all spinning up, all right? And maybe there's an iron atom where its electron spins don't cancel, but the electron spins are making a magnetic field that goes down, all right? So if you have an iron atom that is makes a magnetic field going up, and right next to it you have an iron atom that's making a magnetic field based off its own electron spins going down, well, those two magnetic fields will cancel each other out, all right? If you get a whole bunch of atoms that are all in the same way, all right? And here I said maybe there's 3 of them. And that when I mean a whole bunch, in reality, you know, billions, tons and tons and tons of atoms. If they all kind of go similar in the same direction, they will not cancel out, and they will create what we now call a magnetic domain. So let's imagine I have 3 iron atoms that all have a magnetic field spin going up. Then I would get a magnetic domain that also points up. Likewise, if they all go down in that region, then I'll have magnetic domain there that goes down, all right? So where does this lead? Well, our nail, all right, our nail here has tons and tons of magnetic domains. And that's why we call it magnetic, but it's not a magnet. So a magnet will have all the magnetic domains pointing in one place that will not cancel each other out. Whereas something like the nail has magnetic domains, but you can imagine this magnetic domain is pointed one way because all the atoms are influenced that way. And this one has all the atoms lined the other way. So those magnetic domains cancel each other out. And in this example here, this piece of iron has magnetic domains that are canceling each other out. So it does have magnetic domains. So we say this thing is magnetic, but it's not a magnet, all right? Where this thing of its magnetic domains are aligned, okay? Now, what happens when we do this? Well, that seems pretty crazy because we showed earlier that this wasn't a magnet, and magnets exert forces on other magnets. So if this isn't a magnet, all right, well, now it is a magnet because it's being attracted by this magnet. So how does that work? Well, it all has to do with the magnetic domains. So if we take this magnet and this thing's magnetic field, which is represented by the red lines here, let's say it's in that one direction, that strong magnetic field will make all the magnetic domains here get in line. It has a big influence over. And once all those magnetic domains get in line with this, then this thing becomes a magnet. All right, it becomes magnetized, we could say. Now, if I take it out of this magnetic field, it goes back to its original spins, all right, and it becomes not a magnet, but it has the ability to become magnetized. It has the ability to become a magnet. So some of our materials, while they're not a magnet always, they are magnetic, and they can become magnets. All right. Now copper here, just because it's made of metal, doesn't mean it's magnetic. All right. Even if I take this magnet and bring it near this thing does not have magnetic domains, because if you go all the way down the electron spin level, they cancel out. All right. So this thing is not magnetic. All right. It has no interaction with an actual magnet. Okay, now for one last proof for our current making magnetic field. All right, notice that right now with the current off, the currents. All right, if they were, they'd be sticking each other. But if I can turn this on, all right, just turn on now, the magnetic field produced by the current can align these magnetic domains in the paperclip, and I can pick them up. All right. And then going back to original thing, if I turn this off, then they fall down, which is nice because I can turn electromagnetic on and off. And there's still a little bit of residual magnetism, but you can see the point. All right. And that is why some things are magnets and some things are not magnets. All right. It all starts with moving electric charges, and then if we just talk about this, all right, it builds up to the atom. They got it. The electric spins can't cancel out. Then the atoms cannot cancel out, so the atoms got to build up to make magnetic domains, and the magnetic domains cannot cancel out and build up to each other. And once all the magnetic domains get lined up, then the thing is a magnet. All right. But without magnetic domains, something is not a magnet. All right. And there, now you finally know what makes a magnet, what things cannot become a magnets and why, and where magnetism all starts. All right. It all starts with that moving electric charge. A moving electric charge is a magnet. You got to be able to see those things in the same exact thing. It's not just an electron moving. Electron moving is also a magnet because it creates a magnetic field. All right. And we saw examples of those. We've proven it. Okay. So we will be getting into some equations that, kind of prove those, but that's a different lesson. All right. So thank you for watching, and see you when I see you.